Okay, and then the last section of chapter 10 talks a little bit about some of the applications of acid-base chemistry, and specifically what it discusses is this um, uh, use of and the importance of solutions known as buffers, right? So the first thing we'll do is define what a buffer is. We can define a buffer as a solution that resists drastic changes in pH when acids or bases are added to it. All right, so really you can think of the function of a buffer is to maintain the pH at a relatively constant level. Okay, the function of a buffer is not to get the pH to neutral. The function is to keep the pH where it is. All right, and that's a common misconception that students have at the beginning. Oh, buffers should get the pH to 7. No, buffers function to keep the pH at a relatively constant level, whatever that level is. To give you a simple analogy of how buffers work, right, you can think of a buffer as sort of analogous to the bumper on your car, right? So if you get into an accident or a collision, the bumpers serve to absorb most of the energy of that collision. So you in the middle of the car or in the car itself don't experience the full force of that collision, right? So buffers do something similar. They absorb the full force of the hydroxide or the hydronium that's added from an acid or a base, and as a result, the solution itself is not going to change its pH drastically. All right, and in lab, you actually made some buffers, and you tried to change the pH of the buffers by adding hydrochloric acid and sodium hydroxide to it. And hopefully what you saw was that with the buffer solutions, the pH all changed very minimally compared to some of the other solutions that you used. All right, so buffers are extremely important things. You find them all over the place. They're found in some of the foods and drinks that you take on a regular basis, but more importantly, they actually are found in the blood, where they help maintain the pH close to the optimal pH for the blood, which is around 7.4. Right? So if you remember from class, the pH of the blood is not neutral. It's not 7, right? It's actually slightly basic. And it needs to be to allow all the stuff that resides in the blood to function effectively. If the pH changes drastically from that roughly 7.4 pH value, it can affect the organism, which in most cases would be you. All right, so buffers are extremely important, especially in the blood. So what are buffers actually made up of? Well, the most common components of a buffer, so most commonly, buffers are made from a weak acid and its conjugate base. Right, so for instance here we have an example of a weak acid. This is acetic acid. And the conjugate base is going to be the thing that is lost, that H+, right? So this acts as an acid, gives up that H+, and we have our conjugate base here, which is the acetate ion. And oftentimes you'll see the word or the term salt of the conjugate base. All that means is that there's some sort of a positive ion in there that's going to take care of this negative charge, right? So sometimes it's like a sodium ion or a potassium ion. That's all that means, is that there's a positive ion present as well. So your buffer is going to be made up typically of a weak acid, right? That's the first component, and the conjugate base of that weak acid. And there are equal concentrations of both of those components of the buffer. So let's see how they actually work. So in the buffer with the acetic acid and the sodium acetate, we know now that acetic acid is a weak acid. All right, and that means that it's not going to dissociate much. So if we were to write the equation for what's happening to it in water, right, because it's weak, we're going to have our double-headed arrow, and that's going to give us H3O plus, and then we're also going to get the conjugate base. All right, because it's weak, it does not dissociate much, so that means we're going to have very small amounts of the products, or we're going to have large amounts, specifically of the undissociated acid to begin with. The salt, the other component of the acid, such as sodium acetate, this breaks apart completely, as salts typically do. So complete dissociation. So we're going to have lots of the conjugate base in solution. All right, so what that means then, as a result of having these two components, is the buffer is going to have a large amount of the acid, the weak acid, so H, in this case acetic acid, HC2, H3O2, and because the salt breaks apart completely, we're going to have a large amount of the conjugate base, C2H3O2 minus. And both of those components are going to have functions in the buffer that will help it do what buffers do. So let's take a look at each of them in turn. So the first thing we'll take a look at is the function of the weak acid. And the function of that weak acid is to neutralize any added base to that buffer system. So for instance, if you were to add a base, such as a hydroxide base, to your buffer, the acid part of the buffer, the acetic acid in this case, neutralizes that base that's added. This gives up an H plus to the OH minus to make water, and then when we take the H plus away, we end up with the acetate ion. So essentially what you've done is you have traded a strong base for a weak one. And as a result, the overall effect on the pH of the solution is minimized. Right? It's not that the pH is not going to change, right? If you add a base to something, the pH is going to go up, it's going to become more basic. But what the buffer does, and specifically what the acid component of the buffer does, is it neutralizes that strong base, and in its place, it produces a weaker base. So the overall change to the pH is minimized. The other component of the buffer, which is the conjugate base of the buffer, its function is to neutralize any acid or any hydronium that would be coming from an acid that's added to the buffer system. So if you add an acid, for instance, right, that acid is going to produce the H plus or the H3O plus. The base component of the buffer is going to neutralize that. It's going to act as a base, and it's going to absorb, or it's going to accept an H plus from that acid. As a result, we end up making the acetic acid, which again is weak, and we also get a little bit of water as a result. So additionally, what's happening here is you've traded a strong acid that was added to the buffer system, and instead of that strong one now, we produce a weak one. So as a result, the change to the pH is minimized. Right, so you add an acid to something, the pH is going to decrease, right? It's going to become acidic. But instead of the pH decreasing drastically, right, the buffer neutralizes that strong acid, and in its place, it produces a weaker one. So the pH decrease is minimized as a result of that. So the addition of an acid to a buffer system or the addition of a base to a buffer system will change the pH of the buffer, but the change is minimized because of the components of that buffer system. It's important to note that buffers will only work up to a certain point, right? So if you keep flooding your buffers with a bunch of acid or a bunch of base, then eventually the buffer can be overwhelmed. Right? And then it wouldn't be able to carry out its function. But in terms of what you would experience in your blood, for instance, the changes of the hydroxide and the hydronium concentration due to metabolic processes, the buffers in your blood are perfectly capable of minimizing the changes to the pH. So let's take a look and see how we can identify buffer solutions. All right, so we can go through this and kind of walk you through my thought process and share it with you as we approach this problem. So it says, which of the following combinations can make a buffer? All right, so let's look at A. So A says HCl and KCl. Well, HCl is an acid, yes, but is it a weak acid? And the answer is no. This is a strong acid. Right, so we cannot use that as part of a buffer. If we look at C, right, C has H3PO4, which is a weak acid, right? That's phosphoric acid. So that's one component of the buffer. But remember, the second component has to be the conjugate base of that weak acid. In other words, these two things should look similar to each other, and they don't. Right, so this cannot be used as a buffer system. This is not the conjugate base of phosphoric acid, H3PO4. So we can rule that one out as well. So neither A nor C. If you take a look at the other options, all right, so this is carbonic acid, H2CO3. All right, so that's weak. And then is this the conjugate base? Right, does it look similar to the original carbonic acid? Is it different from it by having one less proton? And the answer is yes. Right, this is the conjugate base. Specifically, it's the salt of the conjugate base, so that can act as a buffer system. If we look at D, this is acetic acid, right, which is also weak. And then this here is the conjugate base of acetic acid as well. Specifically, it's the salt of the conjugate base. Right, so this can act as a buffer system as well. All right, so when you have to identify your buffer systems, you want to make sure that you're starting with a weak acid, first of all, and then you have to have the other component be the conjugate base of that weak acid, which simply means that it just is going to have one less hydrogen than the original weak acid. And that hydrogen typically is replaced by a cation.